Alright, continuing in this series of videos, examining mostly electrodynamics, properties of electrons in this version of this lecture series 802, mostly focusing on what happens to electrons, magnetism, electricity, and it ends with a little bit on photons, which again I don't think are as either electrical or magnetical as conventional physics would claim. So, to the videotape.
And this is what we're going to do now together. I want you all to stand up. And I'm going to make you listen to 3,000 hertz.
Alright, so this is an experiment where he's doing wave interference with sound. And as a primer to comparing it to wave interference in light, where you can demonstrate that there's lots of experiments you can do where the two are very dissimilar rather than similar.
And what I want you to do when I turn on the two loudspeakers, I want you to move your head very slowly and try to find locations where you hear silence. The position of silence is extremely well defined, so don't go too fast, you miss it. Also keep in mind that there are reflections of the sound from the walls and from the blackboard. And so the pattern that I have calculated here is not perfect.
Yeah, it's kind of useless, not a very scientific experiment, blah 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 blah.
But you will see that there will be locations where sound plus sound will give you silence. You are a couple of lousy scientists. You are a couple of lousy scientists. If the separation between a lot of sound and silence is 19 centimeters, that's about the separation of your ears, you dummies. So one ear could be at a maximum, the other ear could be at a minimum. So at least close one ear.
It's hard to even do that against tones like that, so that's another problem too. So, well, whatever.
Go very slowly.
Not enough people in the lecture hall. This whole thing is just a, just really quite useless as science.
Who has found clear locations where the sound is nearly zero or practically zero? Most of you. And you certainly can hear, if you move, that there's an enormous difference in sound intensity. So again, who has found locations whereby you clearly say this is practically silence? Ah, you see them all the way in the back. And the separation, how far you have to move, depends on how far you are away from it.
Didn't seem very authoritative, and well, maybe I don't hear anything. Maybe.
Sit down again. Young was a sound engineer, and as a sound engineer, he was very familiar with the interference of sound.
Apparently not very familiar with Newton, though, because Newton had already done the experiment, essentially. Okay, he didn't do the explicit two-slit experiment, but he did everything around it, the single slit, the single hair. He had already discovered the interference pattern in the form of Newton's rings. And again, it was described as rings, it was described as bars, until Young decided, okay, that's something different. I'm not even saying Young decided. Clearly, it was in the 1800s, early 1800s, and they somehow didn't figure out that this means something until 1930, where they decided, oh, we got to explain these waves.
He knew that sound and sound can make silence. And so in 1801, he demonstrated in a convincing way.
So again, in a convincing way, with an experiment that was completely unremarkable, very crude, used sunlight through two apertures, and you got patterns of little round balls with not monochromatic light, So the red ones, blue ones, all kinds of blending. A very crude example of Newton's rings. So an experiment done 150 years earlier, just ignored, and then it took almost 150 years for them to figure out that Young's experiment means something.
That light plus light can create darkness.
So that's one of the phrases that just should be obnoxious to your sensibilities. That doesn't make any sense. We don't see that you can nullify light. I can plow two laser beams into each other. They don't nullify each other. The energy doesn't disappear. Light doesn't disappear. You can't destroy a photon. It's one of those things that are perpetual, eternal. That the energy of a photon, if it goes into a system, it comes out of the system. It's always alive somewhere. It never dies. So it should be right. Should be something you're saying to yourself that, oh yeah, the only way you can nullify energy is essentially to give it back to an environment. So if two things crash into each other, they give their energy to the environment. The two things could stop. And if they do stop, it's because they released their photons back to the environment again. Their momentum was never destroyed. It was released in some other form of movement. There is no photon plus photon equals no photon.
Would be the nail in the coffin that would demonstrate...
So again, he says nail in the coffin, but I still accept wave-particle duality. This is their hypocrisy, okay? They talk as if, okay, yeah, we can't really prove any of this, and we'll argue, explicitly in one statement. We'll say something like nail in the coffin, and 10 minutes later they'll say something like, well, you can think of it as a particle when you need to, and you can think of it as a wave, you can think of it this way, you can think of it that way. I mean, this isn't an answer to physics, okay? This is mush. This is goo. This isn't a solid foundation to build your physics on. It's a particle, it's a wave, we don't know, except we're sure, but we can't say we're sure because obviously we don't have any evidence. I mean, except it's nail in the coffin evidence, but it's not enough evidence to say Einstein was wrong. It's mush.
Uniquely, that light are indeed waves, and there was still this controversy between Huygens and Newton, as you perhaps remember. Newton wanted light to be particles, but Huygens wanted them to be waves.
Well, this want thing is not a nice way to say it. Newton rationally said things happen for a reason, and coming up with some notion, okay, of waves that don't spread and all the other reasons why waves doesn't make any sense, waves spread, and that from every experiment Newton had done, he kind of saw these as little corpuscles. They were tiny little things that landed in discrete little bits. They didn't do what waves do. So he didn't have a whole lot of reason to think they were waves.
And the way that Young did his experiment is as follows. He had a screen. Don't think of it as this big. You're talking now about extraordinarily small dimensions. You will understand shortly how small. And in this screen are two openings, two pinholes. And light is coming from the left. And think of light as being plane waves. They reach these two openings.
All right, so if he's going to describe Young's experiment, he probably should describe it the way Young did it. So what Young did was took sunlight, and he first put it through a tiny hole. So it went through a little aperture, small aperture, spreading the light, and also technically creating Newton's rings, by the way. And then he cast that light on two more holes, very close together. So again, it's not quite accurate. The straight waves doesn't exist in Young's experiment because he put the light through a small aperture which already created wave functions, technically.
And these two openings, according to Huygens, will produce circular waves.
Right, so the small aperture would have done that too. So circular waves would have gone into the two holes. Just saying.
Spherical waves, of course, three-dimensionally. These openings become Huygens sources, and spherical waves will propagate out in this direction.
Right. And so there's absolutely no physics for that to happen. There's no reasonable physics. Huygens' theory is an infinite number of little waves pop out in front of the waves, and they make somehow a bulgy wave somehow. Where, why would a bunch of little, infinite number of little bubbles create anything other than just another straight wave? I mean, it'd end up being another straight wave, another straight wave. There's no reason to think it would create those bulgy waves. And the only way those are created by fluids is because of drag, because there's friction with the surface, and because the medium has tension in it, and the tension bends the stuff stuck to each other. Because the stuff isn't sand and it can't just fly through freely, it ends up sticking, so it bulges. There's no reason to think photons do anything like that. No good reason.
And so now we have exactly the situation that we had with our sound. Now, if all works well, there should be directions theta away from this line where you see darkness and other directions.
So coincidentally, there's phenomenon that do something that's incredibly simple, which is they move something from this direction to this direction, or double that direction, or triple that direction. So a very simple pattern, on-off at a consistent angle. That's all it is, on-off at a consistent angle. Just about the simplest pattern, the word pattern could be used to describe. You can't make a pattern much simpler than on and off, on, off at a consistent rate. It's the simplest pattern I can imagine, and because two things have it, two separate things in two different places create the same kind of pattern, an on-off pattern at a regular rate and a regular angle, we are to accept that it seems like they must be the same thing. Even though we can know mechanically there's no reason to think they are the same thing. There's very little reason to think they're same.
Where you see bright light. And we are going to do it in a way, we have the luxury of laser beams, so we have very strong light sources, which Young did not have. The way we are going to do it, we have a slide which is completely black, but with a razor blade, two lines have been drawn on it. And so I will draw these lines as white lines, but they're really openings. And there's another one here. And the separation between these lines, D, is 0.088 millimeters, less than a tenth of a millimeter. When you look at them, you cannot even see that there are two lines. Our laser beam.
So, and let's understand, he's not going to give us the dimension of the opening of the slits, but it's assumed to be about a millimeter. So it's pretty close to the same as the width of the impediment in the math, but it's just assumed. So that variable, D, if they were analyzing the single slit experiment, would be the width of the slit. So just understand, these are the little bits, the little maneuvers done to engineer this fit. This doesn't just naturally fit. It's been engineered to fit over the last 70 years.
Has a diameter of about 3 millimeters, which is 30 times larger than this distance. 30 times larger. So what I'm going to show you now, that this is our laser beam, is not to scale. The laser beam is much larger than that. Young's exact setup was somewhat different from my drawing on the blackboard.
Ah, there. So he's conceding that Young's setup has very little to do with this description. Not very little, but I mean, it is substantially different, and you can't play this game of straight waves versus curved waves because that has nothing to do with Young's experiment. It has nothing to do with the outcome of the experiment. So this pretense that, you know, certain kind of waves come in and they do a certain kind of Huygens-y thing, just like sound or something. No, there isn't any exact correlation.
But my drawing simplifies Young's setup and is therefore easier to understand.
Yeah, well, the point is it's a really simple experiment, and you really shouldn't have to simplify. And the obvious point is that Young's version is a cruder version. It's not. You're not simplifying it. You're engineering it. There's a difference. So why not just tell the truth? I mean, Young's experiment couldn't get much simpler. And you're saying it's this nail in the wall proof and nail in the coffin proof and all this stuff. And the truth is that Young didn't even take good enough notes for anybody to even perfectly duplicate his experiment, because he doesn't have any like perfect drawing of exactly what he did.
And so the light will go through some parts of these slots as far as our laser beam reaches, and we are now capable of predicting when we're going to project it.
I don't know. So even that statement, as far as our laser beam reaches, when he just pointed out the laser beam is 30 times bigger than the slit. You know, I mean, if you say the slits are as wide as the thing, then it would be 10-to-1 ratio. So the total of the experiment, the two slits combined, is 1/10 the width of the laser beam.
There. Here are the two slots, which are like so. And so you're going to get interference patterns in these directions, theta, and we can calculate what the position x is going to be there between the maxima.
Right, so it's all about just calculating things that who could care less about where exactly is this and where exactly is that and all that stuff. So therefore we've proven that light's a wave because we've made calculations to do something rather simple, is to say, well, what's the frequency and what's the width of the slits and how far apart are they, and we'll say that's going to determine what kind of angle they're going to leave at. I mean, that's all that's here. The only thing to figure out, there's an angle going to be created. And what's going to determine the angle is the frequency of the light and either the width of the opening or the thickness of the impediment. So you're really just talking, this is the forced surface experiment, and the single slit is the two surface experiment. All you're really saying is when you pass light by a surface, because that's all this experiment's really doing if you think about it, right? You're just taking something like this and you're saying, I'm going to shoot light through this. Well, you have to understand that the photons that are going to be interfering with the circumference are going to be a tiny percentage of the overall light, right? But if I make this thing smaller and smaller, exponentially, like at a 4-time rate, the number of photons that are going to be near the surface is going to increase. So as I make this circle smaller, I at a 4 times rate make the number of photons that went near the surface increases. So you could argue pretty logically, I think, well, maybe the surface has something to do with why the photons leave at an angle. Maybe traveling near the surface of material can cause photons to deflect at angles, to scatter at specific angles. Maybe. Maybe that's not way outside the realm of a reasonable explanation, right? Is that way outside the realm of a reasonable explanation versus Huygens, an infinite number of little wavelets that the photon somehow creates a bunch of infinite number of little waves, and the little waves do calculus, figure out where to land, and then it lands there as a photon? Which seems more probable? That surfaces passing right next to a surface might mess up a photon's path versus, okay, the photon splits in two, creates a bunch of little an infinite number of little wavelets, interferes with some of them interfere with each other. It figures out what the interference means and says, I go here, or I go here, and then goes there as one little corpuscle. I'm just arguing from this position that somehow I'm a fringe lunatic because I just come to the simple conclusion that this is a surface phenomenon, obviously, and it's likely that the cause of this effect is the fact that photons are affected by traveling through surfaces, because surfaces have a bunch of electrons and different ions and different stuff bubbling up from them. They have energy and they're rippling, and that the photons hit the ripples and are deflected. Is that really that far out of the realm of reasonable? Is that something to be mocked for or harassed? Like you're denying the round earth because you deny that their theory sounds a little bit strangled like it sounds contrived versus the simple explanation that there's a mechanical cause. Sorry for the speech, but this is a huge part of physics, and this is a huge conclusion in physics, a huge part of the foundation of physics, and it's a rotten foundation.
And so if that is the screen, and if this is x equals 0, and if this is x1, and this is x2, and
no, let's point out in the single slit there won't be any 0. Okay, there'll just be x equals 1, and then there'll be 2 2's, and then there'll be 2 3's. So again, another change in the way you formalize the formula.
Of course, the whole thing is symmetric. You can always go in the opposite direction. You can now calculate, and you have all the tools. I did it for you in great detail using sound, but you have all the tools to do it now. You know G. I'm going to tell you what lambda is. It's 6,328 angstroms, and 1 angstrom is 10 to the minus 10 meters. So you can calculate.
Right, so it's 632 nanometers.
All the direction theta, for which there are maxima and for which there are minima. Minima means light plus light gives darkness.
So he says it again, he says it 4 million times, but I'm just going to emphasize how that's just hyperbole. I mean, that's just, you know, it's a nice phrase, but we know that the light doesn't go nowhere. That the light actually does get moved to a new location. It isn't light plus light equals no light, or there's no, that can't happen. Okay, so it's light goes to the locations. It's moved to a different location. It's kind of obvious. The light was going straight through the hole, and it's clearly spreading now, and it's doing it in this bar pattern. Even if it just spread, you could understand that, oh yeah, it wasn't light plus light equals no light, because yeah, the light's there. It's just not in the place we thought it was going. It changed its direction, and there is no photon plus photon equals no photon. The photon either goes here, or it goes here, or it goes here. And it doesn't go here, and it doesn't go here, and it doesn't go here. That's it. But there's no broke photon. There's no destroyed photon.
Amazing concept. And you can then, if you know the distance from here to the screen, which is capital L, you can calculate what the separation is as we see it on the screen. And
yes, we can understand that the further away the screen is, the bigger the image is. Yes, we can understand that part.
L is roughly 10 meters. Maybe 11, but that's not so important.
It's not so, 10% error, who cares? Anyway, funny. Yeah.
And so I calculated, and you can confirm that,
I don't know why
you should confirm that,
volume
that the angle theta 1, I will only calculate theta 1, which is the angle then to this point. Theta 0 is of course always 0, right? That's the easiest. I find that theta 1 is 0.41 degrees. That is for maximum.
Right. Okay, so there's your answer. So it'll be 0.82 and then 0.12, and I mean, it's just a multiple of the angle. And the only thing that's going to break that in terms of your measurements is the fact that the angles are presuming a circular, so you have to have a circular screen. You have to have a parabola to put the image on to get the right actual distances. Because you're changing the distance the light has to travel. Obviously it spreads more. So if you have the correct shaped screen, these multiples will be completely consistent. They'll just be a doubling of the angle. I mean, doubling from the original. You just add a multiple of the angle. I don't know how to say that, but a progressive multiple of the angle.
And that means that x1, given the distance of 10 meters, then becomes 7.2 centimeters. So from here to here on the screen, from maximum to maximum, will be about 7.2 centimeters. And from here to here will then, of course, also be about 7.2 centimeters.
And that's completely, though, dependent on how wide those slits are, and none of that's in the math. So the math is assuming a slit width. If I change the slit width, I will change those numbers. So it's not even in the formula, the slit width, and yet it is critical to what you will actually see on the screen. So their formula doesn't even contain one of the key variables, which is the width of the slit.
And in between, you will see darkness. The light from the two sources, 180 degrees out of phase, and that will give you darkness.
See, in the two-slit experiment, you have two variables to play with. You can change the width of the impediment, the middle barrier, or you can change how wide the slits are. And they've destroyed one of the variables. It's just gone, even though it's still critical to how many bars you're going to get in your pattern. So you will increase or decrease the number of bars by increasing or decreasing the width of the slits, and yet it's not in the math. And it's not even stated as an assumption. Clearly he didn't even state what the assumed slit width is.
Let me turn on the laser and turn off the lights. Make sure I have my... Okay. And there you see it. There you see a maximum darkness. A maximum dark.
So unfortunately, in the two, well, I thought this is the X version. It has a much better. It uses a green laser, and it's a much better image. So this is a pretty bad image of the double slit, in the sense that it's not showing the two patterns superimposed on each other. It's not showing the fact that you can have a lot of bars. So clearly the arrangement he's used here is poor in terms of, this is not a very elaborate double slit reveal. And if he had used different slit widths or different impediment width, he would have gotten a much better pattern.
Darkness, a maximum darkness, and so on. And the separation, if I didn't make a mistake, between the maxima is indeed about 7 centimeters. Imagine what an incredible moment this is in your life, that you actually see that light plus light.
You're seeing something almost as bad as Young's. So in that sense, he was true to Young's experiment, because he did the experiment so badly that it looks as bad as Young's version. Inside of each one of those blobs would be bars, and they would have a clear shape of intensity. I shouldn't say it that way. They'd have a clear, more intense in the middle, less intense on the fringes.
Can make darkness. So the waves go
So again, he just says the photon plus photon can make darkness. And again, that's not happening. There's no reason to believe that's happening. All that's happening is that the photons, for whatever reason, are changing their angle, and they're changing it by a consistent amount. It's either 0.47 degrees, or it's 0.8 degrees, or it's 0.11 degrees, whatever. That's what it's doing. All right, that's all it's doing. There's no photon plus photon equals no photon.
Simultaneously through both openings. And each opening
so the photon simultaneously through both openings. So he says, he's saying that we have this nail in the coffin evidence that photons go through two openings, even though there's no reason to believe photons can do any of this stuff, and that somehow, again, they create an infinite number of, this is Huygens' theory, an infinite number of little microwaves, and those little microwaves create another wave front, and the wave front is somehow bowed because of these micro bubbles, which have no reason to bow the wave. So the whole thing is just so contrived. It's just such a pile of let's come up with anything to explain this. It's so distant. How can we make this match water? How can we make this, that's all this is. And they won't even admit they're ether theorists, because this is just an ether theory. Some sort of medium that, forces the light to, constrain its movement, and it's just horrible.
Like a Huygens source. And the net result is that these two waves arrive there on the screen, 180 degrees out of phase, at the locations of darkness. The censor is, of course, that they have exactly the same frequency, which is what they do. Because
well, they have to arrive half phase, not a full length out of phase, the half phase out of phase to be canceling.
we have one laser gun going in, and so the wave goes through both slots. So we guarantee that was the secret that Young understood. You guarantee.
See, you're guaranteed the wave goes through both slots. I mean, this is just, again, so weakly evidenced when it's, again, what's more reasonable? Photon goes through, splits into two and goes through two slits that are so much bigger than the photon. I mean, monster. It's like you going to New York and Chicago at the same time. Like, I'm going to split in half, and I'll go, half of me goes to Chicago, half of me goes to New York. And then when I get there to New York and Chicago, I turn into an infinite number of little me's, mini me's, and you know, the little mini me's start heading north, you know, and start figuring out that, hey, we're getting closer to each other and we're getting further away from each other, and do some calculus and figure out, okay, you should go to Buffalo, or, you know, whatever, Canada, whatever, one of those places in Canada, Sillyville, Canada. And again, I'm the crazy one. I'm the fringe kook, because I say, that doesn't sound like anything like physics. That doesn't sound like anything a smart, intelligent person would come up with as an explanation. That sounds like a UFO fringe, crop circling, you know, magnetic boot wearing, tinfoil, gigantic tinfoil cat in the hat, tinfoil cat in the hat theory. It doesn't sound like something like, oh, normal people should believe this. Like, there's bark on trees. This is so proven. It's just like bark on trees. You can't miss it. Yeah, I can miss this. I mean, it's frightening that I have to make this video. I mean, right now, I'm just saying, I can't believe I'm on a planet so frickin' stupid that I have to explain to them that this really isn't a great answer, is it? Is this really a hard-proven, insanely proven great answer to the question, why is this pattern on the wall? This idea that I split in two and go to two faraway places and mini-me, and is that really a great answer to how I got to Sillyville, Canada?
That the waves are not only the same frequency, but they're even in phase, because they both go through both slots. Now, if you look very carefully here, you will see, of course, that these maxima don't have the same strength. We will understand next lecture why that's the case. They would have very closely the same strength if the opening, where we scratched out the black on the slide, was much, much smaller than the separation between the two slots, so to speak. And that's...
Yeah, you'd have actually bars, and you have a much better pattern, but you'd still, technically. So that's another part of their math that's completely engineered. Is they don't really have very good math for the intensity over distance for different slit widths. So they really have to contrive that one to make any of that work, because by their math, there really shouldn't be 70 bars in the pattern. You know, their math says it should degrade much faster than that.
Separation is 0.088 millimeter. If we make the openings much narrower, indeed the light intensities would be more uniform. Each maximum would be approximately the same strength, but then very little light will go through. And so
right, so if you make it much larger, that's where you'll get more pattern. So that's the irony. He's saying, well, we could fix this if we make it smaller. No, you could fix it if you make the openings much bigger.
It's a trade-off. And the moment you make these two openings, these two slots, larger and larger, you will understand Friday why then the light intensities are not the same, why the light intensity is a maximum at the center and then falls off near the edge. As you see, it's a maximum here, and then the light intensities become smaller.
As stated, again, you can go view the double slit experiment, and you'll see there can be 100 bars of light. not 7.
I've shown you now the interference pattern for sound and for red laser light.
Right, and understand, the sound one makes perfectly good sense. Pressure waves, okay? A force going up meets a force going down. Well, we can understand how those two things could cancel. But there's no explanation here that was in any way reasonable how there was any such scenario happening to a single photon. A single photon somehow goes through 2 slits, mini-me's, interferes, and lands. That correlation is not at all. There's no symmetry. There's no logical staircase here at all.
But imagine now that I did the same with white light. The situation would be very different and maybe even disappointing for you. Let this be the location.
It's not that hard to follow, actually. So I don't see why it's a big deal. You could just use a color filter and then, you know, but whatever. So this is sort of, in my opinion, a waste of time. I mean, these students have already seen the idea that there's these different frequencies of light and they move at different angles, and so it seems kind of like it shouldn't be that hard for them to figure out that the pattern's going to be in different locations for the different color of light. So what's the big deal? Not terribly interesting.
On the screen, so we have x here, and here x is 0. And I want to know where the maxima are in the red.
The only really interesting thing here is that obviously a small aperture works like a prism. I mean, it does separate light. You know, you can use it for that purpose.
Well, that's very easy. There will be a maximum here when this position is L times lambda divided by D. This is when Nancy is 1. And there will also be a maximum here when we have 2L times lambda divided by D. And of course there will be one on this side, same distance. And there will be one here. This is when n is 0, n is 1, n is 2. The red light will have maxima. How about the blue light? The blue light will have maxima here, where L lambda divided by D, but lambda is different. Lambda for blue light is smaller, substantially smaller than red light. So the maximum of the blue will fall here. The maximum of the blue will always fall at n equals 0, together with red.
So understand, this little formula he's using here, L times the wavelength, which is the distance to the target, times the wavelength divided by D, gives you your distance at your target, the amount of distance on the target. L is the distance to the target. But again, the D is an insufficient, an incomplete variable, because we know that not only the wavelength and the size of the impediment matter, but we know the slit width also matters. And it's just completely left out of this. It's a very incomplete formula.
And then Nancy equals 2. The blue will fall here. So this is Nancy 2, Nancy 1, Nancy 0. And here, Nancy 0, Nancy 1, Nancy 2. And so the red and the blue, and therefore all the other colors, live a life of their own. They don't talk to each other. They come in with their own separation in terms of angles and in terms of locations, x. That's the reason why I chose one and only one frequency with the sound. Because if I had exposed you to many different frequencies, many different wavelengths, then the location of silence for one wavelength is not the location of silence for the other wavelength. And so the experiment would not have worked. And that's why it worked so well.
I still don't think it worked very well, but whatever. Fine.
With the laser, the red laser, which is practically one wavelength, and so the minima and the maxima are extremely well defined.
I mean, it might be interesting to use a low tone and a high tone and see if they, you know, clearly there would be, you can make them different enough that you get enough distance between the two where, yes, it's high and then low and then high and low. Just make them half multiples, obviously. Then they would fall on, off, on, off, on, off. Well, blended, not blended, blended, not blended.
If we had done the experiment with white light it wouldn't have been so impressive.
And again, his was very unimpressive. Right? This is the almost one of the most unimpressive two-slit images I've ever seen, which is kind of funny. It's so bad. I mean, I've seen better ones done with pieces of cardboard.
And on the next slide, I show you what you would have seen then. This is what white light would have done. This is a two-slit interference pattern. This is what red light would have done.
All right, and this isn't. So this is a bit deceptive, because these patterns, I think, are actually electron patterns. So this is a two-slit experiment with electrons. It's not photons. Well, I mean, it has it red, green, and blue, so I guess it has to be photons. But yeah, we don't know how this was done. So obviously, this is a completely different pattern. I mean, look how defined these bars are, and look at the funny part where the dark spots aren't dark. You know, they start to get undark. So we don't, you know, he should give us some insight into how this was done, what device this was put through, because clearly this pattern is completely different than what he showed.
Red light is a narrow bandwidth of wavelengths, well-defined black lines. Light plus light give darkness, well-defined maxima, and the blue.
And no defined maxima, though. The center maxima is completely indistinguishable. It's supposed to be 90%, 95% brighter. Well, that's in the single slit. But even in the double slit, it's supposed to be brighter, and it's not brighter.
Notice that the separation between the dark lines, and therefore also the separation between the bright lines, is substantially smaller. Because blue light has a wavelength of about 4,500 angstroms, and red light roughly 6,500. So there's a big...
So the white one is blended because all three colors are in there, and they're all making that blended crap. So that's why it fades so badly. So that's my bad. But again, these other patterns, you can see where the blue light is more intense in the center, at least. So you get some idea that the light should be more intense in the center. But the red light looks even almost all the way across the pattern. But anyway, you just should point out, well, why does this look so much better than your experiment? Why did this come out so much better than yours, Professor Lewin? Why? Why do you show me images of this when you seem to have the right equipment? Why can't you make a pattern this good?
Difference. And so white light would then give you the superposition of all these colors. And so you don't really get a very nice...
I have a feeling this was done with lenses and such, so...
interference pattern of dark areas and bright areas. All the colors begin to overlap. They each live a life of their own.
Let's also just point out that the patterns are supposed to be bright in the center and then fade to the dark and then fade back up to dark light and then fade back to dark and fade up to light. So they're supposed to be quite gradual, and they're not.
What I can do with sound, and what I did with water, and what I've done with laser light, I can also do with radio, electromagnetic waves. With radar, we have a 10 gigahertz transmitter here that we've used earlier in this course. And so I will now show you that with radar, you can also show interference patterns. And the calculation that you see there are absolutely identical.
Right, because it's still the same effect. So you're still just creating the same effect. You're causing the radiation to go through an aperture that is not consistent with its that is, let's just say it's restrictive to what would be the polarization, the divergence of the photons as they're moving through. So for each thing, you can create bigger wavelengths, means you can have bigger holes. But it's still the same idea that what are you doing? You're just confining in a sense. So if you do it with slits, you're confining, and if you do it with two sources, okay, that's like dropping two sources in water, disturbing the water in two different ways. So they all have, there's this little bit of commonness, and they're just extrapolating that the physical mechanism is the same for all these things when you can point out that physically they're doing a different thing. You can't do the double slit experiment in light the same way you can do it in radar. Why? I mean, I can't just take two light sources, all right, and well, because I can't make photons at the same exact frequency, I guess would be one of the issues. I mean, I can't have them on phase. So that's the problem. You can't take two sources and have them in phase. But anyway, well, let's do the radar, and I'll explain how, again, the similarity exists. It's the simplest pattern in the universe. All you're really doing is talking about spreading things and causing them to land in certain locations because they've had an angle change for a reason. In this case, the angle change is going to be because you have two sources, so obviously there's angles.
The only thing I want to remind you of, that the approximation, when you know capital L, that the tangent theta is roughly the same as the sine of theta, is only true for small angles. 5 degrees is fine, 10 degrees is fine, but by the time that you reach 50, 60, or 70 degrees, that approximation is not true. So then you really have to take the tangent of theta. That's no problem, because you first calculate what theta is, because that equation is correct, and then you can calculate always where x is, but then you use the tangent and not the sine. So these are approximations which hold for small angles. And so if now we look at a 10 gigahertz transmitter, that means we have two transmitters, one here and one here. And their separation D is 23 centimeters. You see them here. This is where they are. Here's one and here's the other, 23 centimeters apart. At 10 gigahertz, the wavelength is 3 centimeters. You can confirm that. Speed is speed of light. The lambda is the speed of light divided by frequency. That gives you the
No, it's 1/10 of the wavelength, approximately.
wavelength. And we have here at
Well, 1/20th.
the distance L, which is 120 centimeters, we have here a receiver and a track. So this is x equals 0, and here we can move it along x. And so you can calculate now at what angles, seen from this point, there will be a maximum there. Theta 0 is obvious. Right here there will be a maximum. The two waves, the distance between them is 0. R2 minus R1 is 0. So they will constructively interfere. But there is another angle, theta 1, for which again there will be constructive interference. And you can confirm that I found for these numbers that theta 1 is about 7.5 degrees.
All right, so again, the assumption here is that he's going to create these waves. Now, they're not waves, they're particles, but it doesn't really matter. They're intensities of quanta. The quanta are flying out of both antennas. All right, that's the idea. And the idea is what do we receive when we see what comes through? And his argument is somehow when there's two waves hitting each other out of phase, that they cancel each other and you get no signal. That won't be what's happening, because what's going to be happening is all he's going to do is jam one signal with the other signal, because the only way you can receive the radar is to tune it. And so when the two frequencies overlap, it's like overlapping red light with blue light. You end up, okay, so your frequency, let's say, has a distance of 1 inch, okay, just 3 centimeters. All right, now if I superimpose two out of phase, you can see that now the distance between the little bits is going to be 1/2 inch. All right, if I superimpose two things on each other, you can see that this becomes 4. When I combine two, I end up with 4. All right, so you can sort of see that now there's only 1/2 inch between them. So I've changed the frequency of the signal, so you can't tune it because it's the wrong frequency now. You can't receive the signal. So the signal is still there. The energy is still going to the location. There's no radar plus radar equals no radar. No, there's a strong amount of energy hitting that location. You can't tune it in because it's a different frequency now.
This is now for maxima. And so roughly at an angle which is half that value, you will find silence. Silence means that the two radar waves will kill each other. Essential.
So again, kill each other. All they're going to do is jam each other. It's like if two radio stations 50 miles apart, let's say 20 miles apart, try to send you 20 miles away between the two of them a signal. All right, if they're if they're both on the same sending the exact same signal, no problem. But you can understand that if now you move to a location where you're 25 miles away from one and 20 miles from away and you're off phase, that the two signals can't be received. You won't be able to receive either station. Both of them would be ruined because the two of them will overlap.
For the maximum to be here is, of course, that the two transmitters are in phase. We could have rigged it up so that they're 180 degrees out of phase, in which case that would be silent.
I mean, I think you know this, right? I think you know that there's periods where you're driving in a car and the stations overlap and you lose your signal. And then if you keep driving, you get a new station at the same dial place, because you've gotten far enough away from the jamming signal.
Here, silence in this case means that the radar would kill the radar. But I do use the word silence for a good reason, because the way we rig this up is the same way we did it before. We modulate this 10 gigahertz signal with a 1000 hertz audio signal. We call it
Right, so all they're doing is putting an audio signal on the frequency, so it's like a radio, broadcasting a radio program, and then he's saying, look at the big surprise, when I have two stations broadcasting from different locations, they jam each other. That's not going to be a surprise. What would make this more interesting, I suppose, is if he could put a different signal on each antenna at the same phase. No, that might be interesting.
amplitude modulation. And the receiver, which is here, receives the 10 gigahertz radiation, which is modulated at 1000 hertz. We feed it to an amplifier, we demodulate it, and you will hear the 1000 hertz.
Right, but what you won't hear is the locations where the two signals are now out of phase and have effectively doubled the frequency of the signal.
And so we can also move it along this track here and find the location x1, whereby we have our first maximum apart from the zero, and I found that that is very roughly.
So the other interesting part of this is you know, this theory is that single photons are supposed to be creating the phenomenon. Single photon in a light, you know, and photons and radio are supposed to be the same thing, just at a different frequency. So somehow for photons, they split in half, go through two slits, turn into a wave function, you know, mini-me's, and then do their thing. Somehow with radar, none of that's necessary. Okay, you don't need any Huygens sources. You don't need to cause any wave. You don't have to create any mechanism. No mechanism involved. And you're sending different photons at each other. So it's like two light sources. So in theory, what he's saying, what this theory implies, is that if you could create two laser beams that were perfectly in phase, it's really hard to create photons that are, even a laser beam itself, the light isn't in phase. Well, let's say you take pulsed lasers, you know, maybe you could pulse them at 10 gigahertz and do this experiment. So pulse the lasers at 10 gigahertz and see if you can make them interfere. Because I bet you can't. So I'm just saying that's the huge inconsistency here. Somehow light has to do this whole strangled, go through two slits, split in half, turn into wave function, and somehow radar, nah, you don't have to. Those photons, they can interfere with each other. Different photons can interfere with each other. You don't need any wave functions, don't need any of that complexity. You just create interference with just photons themselves. I'd argue that's a pretty large incongruity. It's sort of a paradox of their theory. Why this paradox? Why this huge difference in function? And I think the answer is my explanation. This has nothing to do with interference. This radar experiment is just jamming. He's just demonstrating how you jam a radio signal. This has nothing to do with any interference anywhere.
At 15.6 centimeters. And you should confirm that using those equations. The equations are the same, whether you deal with sound or with red laser light or with gigahertz. Makes no difference.
So just pointing out that the equation is simple. It's just taking two factors and saying this affects the angle. This creates your sine theta, these two factors. And the rest is just how far away are you. That's it. So yeah, it's a really simple formula. So of course it works for all of them with a little bit of rigging, you know, changing zeros here and doing this and that. But it's really simple because it's a really simple on-off pattern.
And so let's turn now to this demonstration. I will turn on the two transmitters, and here's the receiver, which is exactly at angle theta 0. So there's a maximum. I'm now going to close one transmitter, put my hand in front, and you think about what will be the reduction of intensity of the sound here. If I close one, it's substantially down. You may think that it is down by a factor of 2, because we have only one transmitter.
But it's really down by a factor of 4, and that has to do with the wave function of the signal, the sound signal. So this is an irony here. The sound signal is going up and then down. So it's a sine wave. And what happens is when you multiply this, when you superimpose those waves on top of each other, you increase the side ones substantially. So they've been substantially increased. So they're multiplying by 4. That's the sine thing, tangent thing, whatever. I mean, it's, you know, so it's that circular, it's that same you're enlarging the circle, and when you enlarge the circle, that's essentially the sine wave is a circle, top, bottom. So you're taking the circle and making the circle bigger. So you're doing that circular geometry thing, which is always the square rule. By increasing the diameter, you've squared the circumference. So that's why there's a 4 times increase. But it's only happening to the audio signal. It's not happening to the actual physical photons coming out of the machine. So the machine is actually still producing. The radar receiver is still receiving, okay, half the radar. So he's blocked half the signal. He's taken away half the photons. The receiver is still receiving half the photons, only half. And it's just the audio signal that's 4 times amplified.
Instead of 2. You're wrong. If you think that, you do not understand interference. It is 4 times.
So it's not anything to do with interference. It has to do with the fact that a sine wave is a circle, and you're when you double the diameter of the circle, the amplitudes, you're doubling the amplitude. That means you have to double the circumference. I mean, you have to quadruple the circumference.
Lower when I hold my hands over one. Figure it out for yourself. I'll test you on the final to see whether you really understood that.
Yes, well, see, and he thinks that he's saying, did you really understand that it's something about interference when it has nothing to do with interference? It has to do with sound amplification on a sine wave.
So now the sound is 4 times larger than when I cover one up. I'll cover the other one up. It's down by a factor of 4.
So again, what he should say to the students, can you really believe what I just said? I mean, you do realize there's a certain amount of photons coming out of each one of these horns, right? You do understand that, right, students? There's a certain number. So there's like 1,000,000 coming out of this one and 1,000,000 coming out of this one, and it's equal. And when I cover one up, you really do understand that I haven't in any way stopped the 1,000,000 coming out of the right one when I cover the left one, right? And if I cover the left one, you know there's still 1,000,000 photons coming out of that one, right? So you know this has something to do with a gimmick. And that's what you should be saying. It doesn't have anything to do with wave interference. Clearly, there's no interference. When he has one horn covered, there can't possibly be any interference. It's one signal going to one horn. How can there be any interference? It's one wave hitting the other horn. There can't be any interference. So the whole way this is implied, like, again, I'll test you on the final as if this change in the sound amplitude, has something to do with wave interference when it has nothing to do with interference.
I can cover this one up and then you hear nothing, of course. Now I will move this one to the location where there is destructive interference, which should be about half of 15.6 centimeters. Maybe you have good.
Right. So now all he's done, I mean, I should draw it. I mean, you can really get this, right? I mean, this isn't that complicated. Come on. All right. So let's use the pens as an example. All right. Assume the pens are all even and not differently colored or whatever. So you can understand the two signals are this. Okay? Two signals have this frequency. And what's happening when they're out of phase is they become this. All right, now you see that, right? You see that this frequency is not the same as this frequency, right? This is twice the frequency. So when they're 100% out of phase, as he has them right now, the receiver is receiving this frequency, okay, 20 gigahertz. It's receiving exactly, right? When he's right on perfect half wavelength interference, no, 90-degree interference, he's created a new frequency. The photons from one thing are coming in. At the same time, these are lagging behind. And they're just photons to the dish. The dish just sees photons. It doesn't know which dish they came from. It just sees photons hitting it. Little corpuscles. Little wave lumps, if you want to call them. So it's seeing lump, 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 lump. It's not seeing lump, lump anymore. So if he tuned his radar to 20 gigahertz at that location, if he could tune it, see, you can't tune these dishes. This receiver can only receive 10 gigahertz. It can't receive any other signal. It can't hear it. So he can't even receive it if he wanted to with that dish. He has to use a different kind of antenna. But if he used a different kind of antenna, that could receive 20 gigahertz signal. This is what he'd receive. He'd receive it. So all he has done is jam the signal. I mean, this is garbage physics. This experiment is a piece of garbage. You should, and I shouldn't be the one who calls it out. Physicists should know this is a piece of garbage. They should be able to figure this. Okay, I get. Yeah. I get that. There's no way to tune a wrong frequency. It took Hertz 8 years. Okay, he knew radio waves existed, and it took him 8 years to figure out how to tune one. Okay, even though there was tons of signals coming from space, coming from here, coming from there, they were making as much noise as they could with radio signals. They knew they were creating this energy, and yet they had no way to detect it. And it took them 8 years to figure out how to detect it, because you actually have to tune to it. You can't just detect it all and sense it that way. Now, to some extent we can do that with giant radio antennas, because we can just measure the voltage that we're receiving and call that a signal. And even though it has a ton of different signals in it, we can just measure. There's a lot of noise, there's no noise. There's a lot of noise, there's no noise. So we can do that. But you can only and that would work here. I'm just saying they could do an experiment where they're just detecting the amount of energy hitting an antenna. So they should just put an antenna, stick an antenna, a little piece of metal, and all they're doing really do is to detect the microwaves. And if they move that little antenna across, they'll find out, oh yeah, there's not any difference. I'll get a little less signal the further away from center I go. It'll be loudest when the two horns are pointed, when I'm getting the full signal, and it'll start to degrade a little this way and degrade a little this way, but there will not be any interference bars at all. And that's how they should do this experiment. They're MIT. They should be able to do the experiment correctly.
But I hear nothing anymore. Now I go through it and find the maximum, which is about 15.6 centimeters. Here it is. And the other side, here's the maximum at center. So here should be a minimum. There it is. And I go to the other side, there should be a maximum.
So it's just jamming, unjamming, jamming, unjamming. So where the two signals are one wavelength out of phase, then they're just superimposing over each other like that. And they're both carrying exactly the same signal. The signal is going to be heard exactly the same way. So no problem. You've just doubled the amplitude of this signal, because now you have twice as many photons. Twice as many little photons. And when they're out of phase, there's not twice as many photons being in the same frequency. Plus, you can't detect this. You can't tune this. This is 20 megahertz. Can't tune that. "20 gigahertz.
There it is. So what I have shown you today is I've shown you the interference pattern.
So you've shown us how propaganda works. That's all you've done. You've shown how if you contrive the evidence and bend it and twist it to fit a theory, you can force the evidence to fit the theory. But that's all you've done. You've distorted and perverted reality to create an impression, to create an idea that somehow this is logically sensible, when if you really picked at it to figure out why certain things are happening, and if you looked at the inconsistencies and said, well, why is there a difference between the single slit and the double slit? Why is there a difference between these different experiments? Why do I have to make the D variable the impediment rather than the slit opening? Why do I have to make these changes? You know, how come single photons do all the action in one experiment, and I can put, you know, different photons can create the same effect in another experiment? If they analyzed any of that, they could figure out that this is all just an engineered picture. This isn't reality. This isn't physics. This isn't the truth. It's just propaganda to defend an underlying notion of reality that's based on we have to write in stone these little Einstein, quantum mechanics, Feynman. We have to put all this stuff in stone, and we can never change it. It's just a religion, and this is just the propagandist for the religion. And it's so overt here, like I'm saying. This experiment is so bad. You know, putting an audio signal on it, doing all this is so bad. If you're going to claim radar plus radar equals no radar, then show me that there's no radar. Don't show me that you know, there's no audio. Show me that there's no energy hitting that location.
Of sound, of water, of red laser light, of radar. And at the very least, I hope I've convinced you, as Young convinced the world in 1801.
Right again. Young convinced the world in 1801. He convinced nobody. It took till 1930 before they paid any attention to slit experiments, before it was at all interesting. It was brought up in one of the conventions they had, you know, where all the scientists met and Einstein argued with Bohr and all that crap. That's when this crap became significant. So let's not pretend that Young's experiment was so remarkable. Wasn't even repeated in any real hard sense. The only thing that was done is the French guy, you know, decided to send single photons and see that the same effect happened. But it didn't prove anything, didn't demonstrate anything, and clearly it's completely an unremarkable experiment compared to Newton's single slit doing the same thing. You don't have two slits to create two waves to interfere with each other. You have just one slit, and somehow still you end up with the same pattern. So your whole theory that somehow these two slits are critical, when the single slit does exactly the same thing in the sense that it creates a bunch of pattern. The pattern's subtly different, but I mean, still bars, still on-off pattern. I mean, this is just this is propaganda. This isn't even accurate history. This is not an accurate description of reality. What made this mean something was the fact that Bohr and Einstein argued. What meant it means something was Huygens and Newton argued, okay, and the arguments were concluded on stupid premises. What decided that Huygens was right was the fact that he predicted light moved slower in a medium. When we know the light's not moving slower or faster, okay? It's just taking it longer for the force to move through the medium. I mean, little simple things. So it's right answers for wrong reasons all over the place.
One, that light are waves. And that means that Huygens...
So again, so he says this rhetoric. Again, this is their dishonesty. Pathetic dishonesty. He's going to make this little end statement. Huygens was right. We know that light's a wave. And yet I can play you the clips of him saying, well, it's particles sometimes and waves, and you can think about it different ways, and obviously in different experiments, it's obviously the blah, 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 all mushy. And then he'll say this emphatic statement. You know, it's just it's so deceptive. It's just dishonest to play this game with words. Word games.
Was right, and Newton was wrong. Now that should perhaps not surprise you, because Huygens was Dutch.
Yeah, right. Well, Newton's going to win the day, and you've been on the wrong course for 100 years because you're all just fanatic religious kooks, and you really don't care about the truth. And the fact that you engineer these experiments, and you must know, the whole reason why they put the tone on the radar experiment is because they did, when they were doing the experiment, they're saying, yeah, this really isn't working. How come this doesn't work? We have to make this work. And the only way they could make it work is to do it with this sound tone. Because they know if they detect the actual energy hitting the location, they're going to find that there isn't any pattern. There's no interference. There's just jamming. I mean, it's pathetic that nobody else is saying this. That me, an unprofessional, an untrained, nobody, is the only person who can figure out this deception. The only person who can figure out that this radar experiment is demonstrating jamming, not interference. I mean, there's not one honest physicist out there who will just say, yeah, all right, I concede. We've never done the experiment the correct way, where we actually detect energy rather than a specific frequency. I mean, this is ludicrous that this trillion-dollar industry, millions of professionals, and not one of them can figure this out? This obvious fraud? Not one? All right, well, anyway, this was effectively the video, the video I did this whole series for, was to get to this big lie. And it's such a big lie. And I hope you saw it in the fact that he tried to just force all of these things to fit. He forced the evidence to match the theory. He didn't let the evidence tell you the truth. All right. Till next time.